the notes for 3.3, properties of logarithms. So today we're going to stray away from the graphing, but we're just going to focus on some of the properties that we have with logarithms. These should be pretty familiar to you from Algebra 2, but again, some of the equations that we're going to look at will be a little more complex, so you want to make sure that you really grasp the concept of these properties. So as we relate logarithms and exponents throughout the chapter, we know that they have an inverse relationship. And when you think about the properties of exponents all the way back to Algebra 1, we're going to be able to see some correspondences with the properties of logarithms and how they relate. Addition relating to multiplication, subtraction relating to division. So as we look at the three properties that we're going to deal with today, if b, x, and y are all positive reals, b is not equal to 1, and p is a real number. Those are just some disclaimers, but the real thing we want to focus on are these following statements. First of all, the product property. If you remember, the log base b of x times y can be expanded to be the log base b of x plus the log base b of y. So again, we can take multiplication and separate it out, expand it with addition. The quotient property says that the log base b of x divided by y can be written as the log base b of x plus the log base b of y. Minus, sorry. Let's redo that. Minus, okay? Okay, so division relates to subtraction the same way that you would see it relate with your properties of exponents. So then there's the power property, and this might be the one that you may use the most when we're solving in the next few sections. So the power property says if I have the log base b of x to the p power, I can bring that exponent down to the front of the log as a factor. So then I would rewrite this as p times the log base b of x. So it's no longer an exponent, it is a full-blown factor that we can use as we're solving using algebraic techniques. So in example 1, they specifically want us to express these logarithms in terms of the natural log of 2 and the natural log of 3. We're not always going to take them down to prime numbers, but because of the directive in this example, we're going to take it all the way down and look for those specific numbers, 2 and 3. So in example 1a, we have the natural log of 54. There's a couple ways that you can do this. I'm going to show you both, but I want you to just write down one in your notes. So the natural log of 54, one way we can write this is the natural log of 9 times 6. So if we want to look for 2's and 3's, I know that 9 can be written as 3 squared, and 6 can be written as 2 times 3. So now we have just 2's and 3's, so I can say that the natural log of 3 cubed, because I have 3 3's in there, times 2, is still the same as the natural log of 54. Now if I just want the natural log of 2 to the first and the natural log of 3 to the first, I have to do something with those exponents, so I'm going to expand it with addition and bring the factor down in front, or the exponent down into the front as a factor. So the natural log of 3 cubed plus the natural log of 2 can now be written as 3 times the natural log of 3 plus the natural log of 2. And this would be our final answer. The other way that we can do this, I'm going to shrink this down and show you one other way, just so that you know if you start in a different place as someone else, you're going to end up in the end with the same answer. So some of you might have seen 54 as 2 times 27. So we can do the natural log of 2 times 27, which becomes the natural log of 2 times 3 to the third power. So once again, we can split up the natural log of 2 plus the natural log of 3 cubed, and then the natural log of 2 plus, bring down the 3 as the exponent as a factor, and that's plus 3 times the natural log of 3. Which is the same thing that we got when we started with 9 and 6. Let's look at example B. In example B, they want us to look at division. We have the natural log, which the properties are the same. So let's go back up here in this gray box. These also apply, just so you remember, they also apply to natural logs. No difference there. So the natural log of 9 divided by 8, we can separate with subtraction. So the natural log of 9 minus the natural log of 8. Again, they still want us to end our answer with natural log of 2 and the natural log of 3. So I'm going to rewrite the natural log of 9 as the natural log of 3 squared minus the natural log of 8, I'm going to write as 2 cubed rather than 2 times 4. And then I'm going to bring those powers down in front from using the power property. So my final answer would be 2 times the natural log of 3 minus 3 times the natural log of 2. And the way that we know that we're done is when we just have the natural log of 3 to the first power and the natural log of 2 to the first power. You can still have things out in front being multiplied to them. But this is as far down as we need to take this because we met what they wanted us to do. We have natural log of 3 and natural log of 2. Okay, in example 2, we're going to evaluate each logarithm. So this means to find the value of the log base 4 of the 5th root of 64. We're going to set that equal to x because we want the value and we don't know it, so that would be our variable. Now I'm going to rewrite this as an exponential. Start at the base, and I'm going to loop around with that scorpion tail. 4 to the x power equals the 5th root of 64. So instead of writing the 5th root of 64, I want exponents. And if it's the 5th root, that would be 64 to the 1/5 power. If you can, remember that you want to find equal bases, and if your bases are the same, then you can set your exponents equal to each other. So I can actually rewrite 64 as 4 to the 3rd power, still being raised to the 1/5, and I can write that equal to 4 to the x. From our properties of exponents, 4 to the 3rd and then to the 1/5, we're going to multiply those together. So 4 to the x will equal 4 to the 3/5. And then because the bases are the same, I know that x is equal to 3/5. And that is the value of that expression, log base 4 of the 5th root of 64. Okay, now we're going to look at letter B. 5 times the natural log of e to the 2, or the 2nd power, minus the natural log of e cubed. So I'm going to first pull this 5 back up. I'm going to go in the reverse order, pull it back up as an exponent, but it's an exponent to e squared. So we're going to take this one step at a time. The natural log of e squared, then to the 5th power, minus the natural log of e to the 3rd. So a power to a power, e to the 2nd, and then to the 5th becomes the natural log of e to the 10th, minus the natural log of e cubed. Subtraction can come back together with division. So that would be the natural log of e to the 10th divided by e to the 3rd. The properties of exponents tell me to subtract those exponents. 10 minus 3 gives me 7. So that's the natural log of e to the 7th. What we need to remember is that that is in base e, and the bases will essentially cancel, and my final answer is 7. So the value of that is 7. Now, one other way I want to point out, you could have done this, and again, let me shrink this down. There's another way that some students came up with that was really creative and totally legitimate. So one thing they could do, they saw this first one as 5 times 2, because the natural log of e squared, again, the e's would cancel, and that's just 2, minus the natural log of e cubed with a base of e, those cancel, and it's 3. So they saw 10 minus 3, which was still 7. Using those shortcuts, definitely using those shortcuts we talked about yesterday, made it much quicker. But then again, using those properties, you're going to get the same answer. So whatever is more comfortable for you, whatever you see first, go with that. We just want the right answer. We want to be accurate. Okay, in example 3, we're going to expand. So we're going to go in the reverse order. So if I have the log of 12 times x to the 5th times y to the negative 2, every factor will get separated with addition. So I have the log of 12 plus the log of x to the 5th plus the log of y to the negative 2. Now I'm going to use the power property. The log of 12 does not simplify, plus, now I'm going to bring that 5 down, 5 times the log of x, plus a negative 2 log of y, which as we clean that up, that's going to be the log of 12 plus 5 log x minus 2 times the log of y. Now, one other way, again, just to show you, there's another way you could have thought about it. If you chose to get rid of the negative exponent first and make that the log of 12x to the 5th over y squared, now you're going to have division. So you would still get the log of 12 plus 5 log of x, but then you're dividing by y squared, so it would be minus the 2 log of y, which is the same answer that we got, just taking a little different path. Both correct. Okay, let's look at B. Right now, I would encourage you to stop the video and try B on your own and see what you get. Okay, we have the natural log of x squared over the square root of 4x plus 1. So the first thing we see is division. So I'm going to split this up one step at a time. The natural log of x squared minus the natural log of, now I want powers, so I'm going to make 4x plus 1 to the 1/2 power. That's the same as the square root. Now I'm going to use that power property, and it becomes 2 times the natural log of x minus 1/2 times the natural log of 4x plus 1. And some people kind of look at the 4x plus 1 and feel like they should be able to split that up, but there is no rule to split up what is already being added, so we're actually done with that. Final answer. Okay, example 4. We're going to do the reverse and condense these. We're going to put these back together using those properties. So we have 4 times the log base 3 of x minus 1/3 times the log base 3 of x plus 6. The first thing I'm going to do is put those factors back in place as exponents. So I have the log base 3 of x to the 4th minus the log base 3 of x plus 6 to the 1/3 power. So division comes back together with, subtraction comes back together with division. So I have the log base 3 of x to the 4th divided by the cube root of x plus 6. And if you wrote it with a rational exponent, that's okay too. You could also have the log base 3 of x to the 4th over x plus 6 all to the 1/3 power in the denominator. That's fine as well. So, happy ending there. Either answer is correct. Okay, let's look at B. Again, try to pause the video and see if you can go get an answer to this yourself. See how well you do. Okay, we have 6 times the natural log of x minus 4 plus 3 times the natural log of x. So again, I'm going to begin by putting that factor back in place as an exponent, working backwards. So the natural log of x minus 4 to the 6th plus the natural log of x to the 3rd. We want to put those back together. Addition comes back with multiplication. So I want the natural log of x to the 3rd times x minus 4 to the 6th. And you don't have to put outer sets of parentheses around there, but if you do, it's not wrong. Okay, so hopefully at this point a lot of this looks familiar. Again, the concepts are not going to change. The equations may get more difficult to work with, absolutely, but just kind of stick to those concepts and just push through. Be sure to check your answers as you do this homework. Sometimes the answers can look kind of scary, but at the end of the day, you kind of check and you see that you're right. So make sure you check those as you do these. The last thing we're going to talk about is the change of base formula. So the reason that we have this is if we need to rewrite logarithms in terms of different bases than they begin with. We've really, in Algebra 2 and in Pre-Cal, we just kind of skim the surface of logarithms, but there are definite uses for them, and so sometimes we need to rewrite them in terms of a different base. So we're going to use the change of base formula, and you may or may not remember this. If we have the log base b of x, that is the same as the log of x over the log of b. Now, the majority of the time that we see this, these will be the common logs. Our purpose is really to do the common log of x over the common log of b. Also, this second formula or algorithm here just lets us know that we can do the same exact thing using natural logs. The properties hold true whether it's a common log or a natural log. One way to remember this, Often if students are going to make a mistake here, they'll put the wrong value on the top. So kind of remember the X is the bigger one, it's going to stay on top, and B is the base, and that stands for the bottom. So if that helps you remember it, just find a way so that you don't mix those up. It's kind of a simple thing, and then it's really frustrating when we just get them backwards. So make sure you practice that plenty of times. Evaluate the following logarithms. So what we're going to do is we are going to plug this into the change of base formula. So that's going to be the log of 5 over the log of 3. 3 is the base, and it goes on the bottom. So the log of 5 divided by the log of 3, we're just going to put that into our calculator. The other thing, you might want to check this out just to confirm and just so you know it's true, try doing the natural log of 5 over the natural log of 3. It's going to give you the same answer. It is 1.465. So the log base 1/2 of 6 is going to be the log of 6 divided by the log of 1/2. So as I look at this and I evaluate, you could also plug in the natural log of 6 divided by the natural log of 1/2, and that's going to give me negative 2.585. Okay? And this should be familiar from something that you've done again in Algebra 2. This example, number 6, is something that will be new. It's kind of cool. We're going to simplify the product of these two logs. We're going to write them as a single logarithm and use that change of base formula. So if we look at the first problem, we have the log base 2 of 7. The change of base formula, we'll put this in terms of common logs, and that gives me the log of 7 divided by the log of 2. Then we're multiplying that by the log base 15 of 2, and if I write that using the change of base formula, that's the log of 2 divided by the log of 15. When you look at multiplying fractions, remember you can cancel these factors diagonally. So the log of 2 cancels, and you're left with the log of 7 over the log of 15. Now the direction said a single logarithm. So if we take this, looking at it as a change of base formula and go in the reverse order, that would be the log base 15, because it's on the bottom, of 7. So this takes us from multiplying two logs with different bases down to one single log. Okay. And that concludes the notes for 3-3.